Hi folks, Joseph Kursky here. Let me show you how I teach about ocean landforms. Now, hills, canyons, plains, and other landforms do not end at the coastlines where land meets ocean. By contrast, the oceans and larger lakes of planet Earth can be better understood by examining their underwater forms. So we're going to explore ocean floors in this 3D scene. It's part of the ArcGIS platform from Esri, and it's the 3D scene viewer. So notice one technical note here. I saved this in my own ArcGIS account. But when my students open it, they don't need to sign in. Notice the sign in button on the upper right. They don't need to log in to explore the ocean in the ways that I am guiding them, but not directing them, guiding them toward. So let's start with this ocean floors 3D scene. Now sure, if they sign in, they can save things, they can draw and save those drawings, etc. But I just want them to explore and understand and appreciate the ocean diversity. So we're going to use the ocean base map here as a base map. This base map is wonderfully rich and it's got subsurface feature names, it has landforms, it has depth. It's important to know the units that you're using. These are in meters here, and is the highest resolution global ocean base map available. It's absolutely fabulous. Now the 3D scene begins, if I reload this, it begins southwest of Svalbard, north of Norway, where the ocean trench changes direction from north-south to northeast-southwest. Notice right here. See that? Right there. Fascinating. We can rotate this so we can get a better sense of what I'm talking about here. Now you can see the change in direction right there. And here's Svalbard up this way. Now we want to toggle layer ocean locations for lessons on and off here. So that way we can turn off those big place markers that I have. Notice how flat the Barents Sea is to the east of Svalbard. Let's go over there, the Barents Sea. Notice how flat it is. Now using tools, we can measure the area of the Barents Sea. So let's go ahead and go to Tools, and we have a couple of different options here. We're going to measure area though, and we also want to pay attention to our units. We're going to measure in metric, but what do we want here? We're going to measure, let's just draw, it's going to default to square kilometers, which is exactly what I want. If I didn't want that, I could change those at any time. So we're going to measure roughly around the Barents Sea. Okay, 757,000 square kilometers. Now the size of France is about 643,000 square kilometers. Let's go ahead and pan down to France here. And so I want the students to compare, hey, that's a pretty big part of the sea. Now, one of the reasons why I like using 3D scenes for ocean exploration is because you don't get that distortion like with the Mercator web projection. You've got a 3D globe here, so your measurements are more accurate and you get a better sense of exploring the Arctic and the Antarctic regions. So is the Barents Sea larger, the same size, or smaller than France? Well, according to the measurement I outlined here, and I was pretty conservative in my measurements, it looks like it's slightly larger than the entire country of France. Now then, one at a time, I want to have the students examine other locations by selecting these rectangles at the bottom of the 3D scene. So, conduct research to examine and determine why ridges from the Peru-Chile trench are at a 90-degree angle. Why they extend at a 90-degree angle? Look at these. Not quite 90 degrees there, but here it's almost 90 degrees. And that's just fascinating. Here's another one. So I want the students to conduct some research on this. Plate boundaries can get complicated, no doubt, especially near margins of continents, as you can see here, manifested by the subduction zone resulting in this trench, especially as it curves. For example, this Arica Bend here, right in here. Fascinating. Faults perpendicular to the direction of the main fault, the Peru-Chile trench, are transformed in ocean floor tectonics terms. Changes in the direction of force occur here as the plate to the north has more room to maneuver. Stress is relieved in multiple directions, including perpendicular to the main direction of the trench. Some ocean features follow a gently curving arc. Let's examine the South Sandwich Trench. Zoom in, find, and note one depth reading in that trench. So I want the students to actually go in here and take a few of these readings with these depths that are right along the South Sandwich Trench here. Here's one of them right there. Fascinating. That's pretty deep. Okay, so they're examining these depths. How much deeper is the Mariana Trench than the South Sandwich Trench? Okay, well, we need to go to the deepest trench of all, and that is the Mariana Trench. So we're going to go there. And this moves us to there rather rapidly, but if we didn't know where that was, let's say we're 13 years old, we're going through this lesson, you can always zoom out and look at all of the place markers that I have. So here we were looking at the South Sandwich Trench between South America and Antarctica, and now we're up at the Mariana Trench. We could zoom there right here, or we could use these rectangles at the bottom, which resulted from my saving the 3D scene when I was signed in to my ArcGIS Online account. Okay, so there's the Mariana Trench, and we can see, wow, that's pretty deep. Look at these colors here. That's indicating the depth of this. And here's a depth reading, 10,994. This is in meters. So, gosh, 11,000 meters to, how about feet? That's 36,000 feet. That's deeper than the height of the Mount Everest. So that's pretty deep. That's pretty deep. That is indeed the deepest part of the ocean. So now we're going to navigate, as I have in my directions to students, which are actually right here. That's my directions. And it's also going to be part of my new Spatial Thinking with GIS book. The 90 East Ridge. Okay, let's go there. Using, again, tools, we're going to measure the distance, measure the length of the 90 East Ridge. This is a fascinating, look at that. Look how straight it is. All the way from, let's say the students didn't know where this was. Okay, Myanmar, almost due south to quite a bit down to the southwestern edge, if you followed it due east from Perth, of Australia. Interesting. So there's the 90 East Ridge. And we're going to look at the measurement tools, but this time we're going to measure a length. So let's go ahead and notice how it curves because we're on the globe and it's the Great Circle route. So longer distances result in an even more pronounced curve, which is another reason why I like using globes for long distance measurements. So, okay, 4,400 kilometers. Interesting. That's pretty long. New measurement, 4,400. What about all the way across Australia? 3,900. This is longer than that. Interesting. What about somewhere close to the home of where a lot of students that I'm teaching are, across the continental United States? How far is that? Ish. 4,100. So this is longer than any one of those. Longer than Australia, longer than the continental U.S. This 90 East Ridge. But probably most students haven't heard of it, which is one of the reasons why I like bringing these out in these wonderful web mapping tools that we've got at our fingertips. Now, these bookmarks in the 3D scene represent a tiny fraction of the fascinating ocean that you could examine with your own students. Consider examining features such as mid-ocean trenches, right? We could examine one of those. Most famous one, of course, is the Mid-Atlantic Ridge up here. Yep, going right through Iceland, of course. Hotspot volcanoes. Well, what if we looked at Hawaii? And what does the ocean look like off of the coast of Hawaii? There's long seamounts also, as you could bring that out. Hawaii is really quite long when you consider all the seamounts, right? The islands are just a tiny fraction of the length of the thing. But look at this. Look at this. This is fascinating. Look at that. And then why is this seamount there? Is that the next island? Have the students think about that. One of these two right here. There's a couple of out here in this. How far is that? Right? We could say, oh, okay, well, from the coast, new measurement, from the coast, that is 36 kilometers only. This one is 129 kilometers, 126 kilometers. So you could look at other plate tectonics related features as well. For example, you could look at volcanoes and earthquakes that have caused tsunamis. Lots of things you could look at here. You could look at ocean chemistry with the ecological marine units. There's so many things that you could do here, but I hope this is helpful, and you've got the URL so you could do exactly what I'm doing right now and have your students look at our fascinating oceans. And despite the detail of this map, this oceans layer, look at that trench. This is what's great about mapping. You see things, new things all the time that you hadn't seen before. That's a deep one right there as well. Wow. Off the east coast of Papua New Guinea. Interesting. Are those subduction zones, spreading centers, transform boundaries, and of course that famous one northeast of New Zealand, learning right here. But you could do exactly what I'm doing and much more with these fascinating tools that allow students to explore, ask questions, do inquiry, problem-based learning, think spatially, holistically, and critically. Thanks for being with me. Get out there and explore.